So similar to box plot, we have histogram that helps us study the dispersion of data. So if you want to understand how spread is your data, box plot alone won't really be helpful. We actually need to use a couple of other statistical measures to understand how spread is your data. So in that scenario, with the help of a histogram, we can conclude a couple of statistical measures like first variance. Variance is the fundamental measure of data dispersion, and we have standard deviation which follows from variance. Standard deviation is the square root of variance. So in a nutshell, if you take up any problem in statistics, the most popular and the most widely adopted statistical measure to explain data dispersion is standard deviation. So whenever you see any statistical example and people are talking about data dispersion, standard deviation is the de facto statistical measure used to study deviation or data dispersion. Now, along with variance and standard deviation, we have coefficient of deviation. So coefficient of deviation, if you look at the definition, it would be a measure of data dispersion divided by the mean. A more simple or a more layman explanation of coefficient of deviation would be coefficient of deviation is defined as a standardized measure to define standard deviation. So I'll give you an example to make this simple. So let's say if you have an example where I'm saying the average age of students in the classroom is around 25 and the standard deviation is around 5. So with these two numbers, you'll kind of construct a lot in your mind to study the data distribution because you have a measure to understand dispersion and you have the mean or the average age for that sample. So the standard deviation made sense because you had an idea about the mean. But what if I would just give you a number like, let's say, okay, the average height of students in the classroom has a standard deviation of 7. So without the mean, like if you have no idea about what is the mean height of all the students in the classroom, just standard deviation won't really be, like you won't be able to make sense of this number. It's not really very interpretable. Only with the mean, only when you have access to the mean, that's when standard deviation becomes more meaningful. So to make that more interpretable, we have a structure or a standardized way where you can express this metric in a percentage format. So what if I tell you uh, the average height of students in a classroom has standard deviation of 40%. So this 40% is a number which is tangible so that you can actually kind of visually construct something in your mind to understand how dispersed is your data. So that's basically coefficient of deviation. Coefficient of deviation is calculated by dividing the standard deviation by the mean and multiplying it by 100. So you get a number which is represented as a percentage. Similarly, we have skewness and kurtosis. Skewness is a measure of asymmetry or symmetry in the distribution of data. Now, there is an important term which you would cover over here that's called normal distribution. Probably this is the first time you've heard about it. But in the upcoming slides, we take a detailed note on understanding what is normal distribution. But then for now, I can give you a simple example which will help you understand how is data distributed for a normal sample size. So if you consider, let's say the height of, let's say you have an example where you're calculating the height of all the citizens of a country. So you want to say average height of men is around 5 feet 7 inches, and the average height of women is around 5 feet 5 inches. And if you go for a plot, the overall plot for the entire sample or the entire population kind of represents a bell curve, where let's say this is the midpoint and this is the range, which is like the area where maximum people would have their height, and then a couple of outliers over here. So majority of the samples kind of fall towards the middle. That's why we have a bell kind of figure, and this is called a normal distribution. Now, coming back to the previous example or the statistical measure we have been talking about, skewness is a measure of symmetry or asymmetry in the data set. So if you look at this example, this is symmetric. Now, if we had an example where we had a plot and we have a structure like this, so we understand that it's not symmetrical and the data is skewed towards one end. So there's less amount of data towards the right and there's more amount of data towards the left. Or we could have something different. We could have a plot like it is skewed towards the left, but it has more amount of data towards the right. We can see that, okay, fine, majority of the data falls in kind of this section, and little bit of data falls in this kind of section. So if you come back over here to the main example, we can understand that skewness is a measure of symmetry or asymmetry. How symmetric is your data? If your data is skewed towards one end, can I have a number which will help me understand how skewed it is? So looking at the histogram, definitely will be able to interpret that. But then how much you want to tangibly boil that down to a number to understand, okay, how dispersed is the data? That's when we have skewness as a measure over there. Similarly, you have kurtosis. Kurtosis is a measure of whether the data is peaked or flat. So if you come back to the same example, we can have a simple plot that let's say I'll first draw a normal distribution. And I want to draw a curve which is actually a representative of kurtosis. So the curve might be flat or the distribution would be peaked. So I'll actually understand, okay, this might not be a more appropriate one. Let's have an appropriate one. An appropriate one would be something like this. So you can actually look at this and figure out, okay, in the first scenario, when it is really peaking at one point, we can understand that kurtosis is high. It is actually peaking. In the other end, we have a scenario where the distribution is kind of flat. That's kurtosis. Kurtosis helps us understand whether your distribution is looking flat or is it looking peaked, peaked at one, peaked for a specific range of values. So coming back for a quick recap, with the histogram, we can understand a couple of simple statistical measures like variance, standard deviation, coefficient of deviation, skewness, and kurtosis. With these numbers, you can actually understand how spread is your data. Like you can actually figure out the dispersion of data visually using a simple tool, or you can actually have these numbers tangibly printed or and then correlate them to a mental plot. Let's take a simple example to actually go ahead and calculate variance and standard deviation and coefficient. And then we'll actually look at a simple histogram to see how can we interpret things just looking at the histogram. So we go back to the tool. Now let's take a very simple example to calculate variance and standard deviation first. So I'll just take a simple number. Let's say we take a sample of 5 numbers, 2, 4, 6, 8, and 10. I'm restricting this example to even numbers so that the calculation becomes easier. Now, if you want to calculate variance, you can calculate variance with a simple formula as summation of I is equal to 1 to n being the sample size, mu minus x of I. Mu is the mean of the sample upon n minus 1. Now, in this case, we use n as a denominator when we are considering the population, and we use n minus 1 when we are using a sample. Now, the difference between the two, you'll mostly deal with a sample in any sort of analysis. There are cases, definitely there are cases where we have the entire population for consideration. But then consider a scenario. Let's say you are trying to understand what is the average height of men in India. So you can't literally go and calculate the average height for a billion men, a sample of billion size. You'll actually take a small sample, which is a true representative of the entire population. So you probably take a sample of, let's say, 10,000 members and then use that as a statistic to infer some ideas about the entire population. So in cases when you have the sample, the denominator would be n minus 1. And in cases when you have the entire population, the denominator would be n. So in this case, we use n minus 1. So let's do the math to actually calculate the variance for the simple sample. I'll use this calculation over here. Now, putting these numbers into the equation, we first need the mean. The mean can be calculated as mean is equal to, it's a simple addition of all the numbers divided by the total number of elements. So that would be 2 plus 4 plus 6 plus 8 plus 10 divided by 5. So this would be 2 plus 4, 6, 6 plus 6, 12, 12 plus 8, 20, 20 plus 10, 30. So that's 30 by 5, which is 6. So the mean is 6. So we have a number over here, first number. We can say mean is mu, that is 6. Next, we can calculate the variance. So putting the number into the formula, we will say 6 minus 2 the whole square plus 6 minus 4 the whole square plus 6 minus 6 the whole square plus 6 minus 8 the whole square plus 6 minus 10 the whole square. So the moment we have square and divided by n minus 1, which is 4. So the moment we have square, there are no negative numbers. They become positive. So in this scenario, it will be, the first one would be 6 minus 2 the whole square, that is 4 square, which would be 16. Second would be 6 minus 4, 2, the whole square of 2 is 4, plus 6 minus 6 is 0. Again, 6 minus 8 minus 2 square is 4, so we have 4. And 6 minus 10 is minus 4. Minus 4 square is 16. We have plus 16 divided by 4. And this would be 16 plus 4, 20. 20 plus 20. That is the first 16 plus 4, 20. And then again 16 plus 4, which is 40. So 40 by 4 would be 10. So we can say the variance is equal to 10. We have another metric. Now we need to calculate standard deviation. Standard deviation is simple. It's the square root of variance. So standard deviation is equal to the square root of variance, which is the square root of 10. So square root of 10 would approximately be 3.16. So 3.16 into 3.16 would be around 9.9. But then for simplicity, let's assume 3.16. And finally, we have one more method, that is coefficient of deviation. That can be represented as 3.16, which is the standard deviation, divided by the mean, that is 6, into 100. So this would be approximately 50 to 52%. Let's take a simple number, 52%. So we have three numbers. Let's say coefficient of deviation. We have this number as 52%. We have variance as 10%, and we have coefficient of deviation as 3.16. My apologies. Let's just clear this. We have coefficient of deviation as 25%, and we have standard deviation as 3.16. So we have the first three numbers. Now, just interpreting these numbers, just try and understand how do these numbers make sense. So you have a sample for whom we have, let's say the mean is 6, variance is 10, standard deviation is around 3.16, and the coefficient of deviation is around 52%. So if you look at the numbers, I'm saying mean is 6 and coefficient of deviation is around 52%. And you can actually understand kind of how does data look like. So it's 50%, half of the numbers will be actually towards the left and half of the numbers will actually be towards the right of the entire sample. It might look kind of a very simple plot, like a very simple straightforward plot. Like this is how you try to make sense of these numbers. Similarly, let's look at the normal distribution. So when you're talking about skewness, let's say we're talking about skewness. So we have a simple graph which might be a representative of the normal distribution. Now in this case, it's normally distributed because this will be the midpoint. But then if in case you don't have a normal distribution, you have a skewed distribution, you will have something like this. In this scenario, you can see that your tail is towards the right. So you have a skew towards your right. That's when we call it positively skewed. Apologies with my handwriting. I will say positively skewed. And in another example, let's say we have, let's say over here itself, I'll use a different color. I have a number where I have the axis, the number skewed towards the left, which is the negative part. Now this would be negatively skewed numbers. Negatively skewed. And finally, we have kurtosis, which can be represented using a peak or a kind of a flat distribution. So with these metrics, we can actually understand how spread is the data. 5 simple measures with a histogram. Now, if you look at a histogram, a simple histogram can be represented using bins. So let's say we have bins which can be defined with simple numbers, and this is how this histogram would look like. So this can kind of help you understand that this is a very normal sort of distribution. If you had an histogram which kind of represented a different shape, you can get an idea of how skewed the data set is. So this would be the kind of curve you have. So coming back to the crux of the topic, we've looked into basic numbers like minimum, maximum, mean, median, range, quantile using the box plot. And to understand more important or more advanced measures about the data set, we have a histogram which will help us understand variance, standard deviation, coefficient of deviation, skewness, and kurtosis. So the visual tour I gave you is a simple example just to give you a visual experience about how these different measures look like and how are they calculated. But how do we do this in Python? That's an important thing. So let's move on to Spider. We'll take up another simple example and we'll see what kind of functions are available to actually understand the data for a numeric attribute using these different statistical measures in Python.